Hi, hello everyone. Let's look at week number 75 and the solutions in the Raku programming language. So we start with task 1, which is called coins sum. You are given a set of coins at C, assuming you have infinite amount of each coin in the set. Write a script to find how many ways to make some $S using the coins from the set at C. Right, so there are coins like 1, 2, and 4. And the sum is 6, so there are 6 options how we can make this. Right, so this is quite clear. And let's look at the solutions. And actually, this time the solutions are really different. And some of them are quite complicated. So let me start with my solution. At least I understand what happens there. So I've got these coin types, basically, right? So there are different coin types, the amount that I want to collect, and then I prepare the wallet. And I will put to this wallet like the coins that I can use to get this amount, at least in theory. So I'm looping over the coin types, and I will just duplicate the coin as many times so that it's not exceeding basically 6 here. So I'm using integer division, so I will get 6 coins of 1, 3 coins of 2, and 1 coin of 4. Even if I cannot use 4 directly, like to get 6, I still can add something else. So this is the wallet, so I'm using the append. Probably you can make something smarter and make these 2 lines written in 1 line, maybe. Yeah, just try. But after that is just really a straightforward combination of a few method calls, which is the combination. So I combine all the coins that in my wallet in all possible combinations, and then I just grab everything which basically satisfies the condition that the sum of those coins is the desired amount. The only thing is that there's this unique thing, and so because combinations give you some combinations, because like for example there are 6 unit coins, so I need to only unique combinations in the output. The only thing I don't like here is this. So to get the unique combination, I'm just creating a string out of that list, and I compare strings. Well, not me, but Raku compares strings to get unique original items. This one can be done better, and actually we will see a few examples in other solutions. And after that I will just, if I will run this, I will get these. Right, so let me run my solution, Raku ch1. So here are the solutions. Probably the only thing is that I don't print the number of solutions, but nevertheless it's there. Right, so let's go next. Next is Arne. And this is his solution. So first of all, in the signature of the main function, we have this non-negative integer where the sum is at least 1. Then we collect the coin types from the input. We need at least 1 there, and some additional restrictions just to make this perfect. Right, so we get unique coins. So probably because here. Actually, probably you can get this condition and move it here so that you have to enter unique coins, right? But yeah, nevertheless. So, and then, right, so you're appending source. Basically, this is what I called wallet in my solution. Basically, it's the same. So you're just repeating the coin n times, where n is this division, integer division. And after that, I skip verbose block. After that, we take combinations, right? And from this source and grab, basically, that's even better than my solution, right? So I used reduction operator with $_, but yeah, so yeah, indeed, you can just use .sum, which is simpler, definitely. And again, but okay, so in this solution we take unique after everything, and I see, so there's a different thing. So we're using the with instead of as, and the equivalent check for equivalency, right? Right, but still I think there should be even better way to to get a few lists and to basically only pass unique lists there. Okay, nevertheless, so let's run this solution. Raku Arne Raku 1. So what we need in the input is first the amount, and then like 1, 2, 4, and here is the solution. Okay. There's also no it's the number of solutions is not printed here, but the solutions are exactly the same, and there are 6 of them, so it means the result is correct. Okay, I will skip Jan for a moment because his solution is really complicated, and I hope not to forget to go back. But Jason is now right. So what we are seeing here, so this coin combinations function is called with 2 named parameters, so we pass named arguments, the sum, the desired amount, and the coins as a list. Right, so here is the coins where all of them are positive, and the sum, by the way, sum also should be positive, I believe, right? Okay, then it's combinations. In these combinations, what we have here, so we have an array where the first element is 1 and all the rest are zeros, and we repeat these zeros to achieve the sum. So basically, if sum is 6, then we have 1 and 6 zeros, right? And this flattening makes this array like an array, yeah, in regular sense. Right, then we scan the coin types. Coin is then inside this loop. We have another loop, and we loop over all the combinations. And what we're doing here, I don't understand. Well, I mean, I understand what's written here, but I don't quite understand the algorithm behind that. So we're taking the combinations at position I, and we are scanning it through the coin. So the counter $I starts at the coin size, right? The coin amount, and then we increment this by something in the previous position, right? So yeah, and after that you just take the last element. So what I want to do is maybe just to run this function and print the combinations like on each iteration. Say combinations, and maybe even immediately here, right? Right, Raku to Raku. So yeah, so see, so this is the initial combination set, the array of zeros plus 1 in the beginning, and then you fill this. So you like so there's a few iterations, well actually 3 iterations here in this loop, and we fill this array with something, and for some reason the last number gives us the result. Yeah, actually the result is correct, that's correct, but we don't see like the combinations themselves, right? Actually it was not maybe quite expressing the task itself. So let's read it again. Write a script to find how many ways you make. All right, so basically the only thing you need is to print 6, so the result is formally completely correct. Good. Okay, let's go next. Where is it? So we took Jason. So yeah, again, I will skip Luca, and I will go to Mark and his solution. That's an extremely interesting solution in the sense that it's really unusual one. So we see, so let me just copy this to the text editor. Well, at least we have some syntax highlighting, well, not that big, but still. So we see, so this program just creates the nested loops needed to create the combinations and then executes the code. So that's the point. So what we have here, so basically just look at the last line. It's eval of some something, of some string, and basically this string obviously contains some other Perl 6. Oh my god, I said Perl 6, some other Raku code, and right, so this is so yeah, I'll run this program to just look at the code, and also notice that as soon as you have eval, you will get the warning from Rakudo. So to eliminate this warning, you have to have this instruction, monkey see no eval. Right, so maybe let's just say eval before evaluating it. And let's run this program. Raku T, what do we need? We need basically the same thing. So we need the amount 1, 2, 4. Right, so this between here and here is the program which is executed by Raku. So first we prepare this and see. So if you will count, there's one loop, there's loop number 2, there's loop number 3. They are different, like this line appears here and like 2 similar lines appear there. And for example, if I will have like only 2 coin types, I will have only 2 loops there. So we see, so it differs depending on the input coin types. Right. Good. And let's look at the result in our original data. So there are 6 combinations, and the combinations are here. They are exactly the same combinations as we saw in previous solutions. So I believe this is correct. But maybe just try to look at how it's implemented. So we start with some array for results, and then for coin types we iterate over them. And right. So we are mapping some coins from until up to current position in the loop. This is the sum stream. The out stream is so maybe we can look at the program itself. So right, so there's some lack of indentation, unfortunately, but we can Perl 6. Still this editor doesn't know about Raku. Right, so that's the loop. So there are 3 nested loops. I see. So basically now I understand what happens there. So I probably need to do this to understand how this works. So if you want, you can do it like this, of course. So there are 3 nested loops for each coin type. So C0, C1, C2, and inside we have something, and we break the loops as soon as we go over the desired amount, right? Maybe we can start with the simple one. So if v0, what is v0? This is the thing that we loop, the loop variable, right? If it's this one, then we add this thing to the result. So so if we can just use this coin, only this coin, and we can collect the amount, we just add this coin a few times, right? And if that's it, so we start with another coin, right? So if you already cannot add any more coins to this solution, on this step we continue. If we can, then we try to add other coins, I believe, right? So so we try to so we try to add another coin so that this new addition together with the coins on the previous step gives us on the previous step we can also have the situation when there's no coins added, right? If this is 0, where it gives the combination and so on. That's really an interesting solution. So it's kind of straightforward. You create, so basically this program is the straightforward program. It tries all the, or just try to use the coins and try to collect the amount, but this is not that straightforward, so it prepares that straightforward program. Really interesting thing. So I believe there should be a couple of loops, right? But there's no loop like directly. There's a map. Inside that map, there's another map which we use in unshift. Good. Really interesting. So, but you have to be proud if you can create this program. And also notice that Raku is quite, so basically you don't suffer from any slowness of this program. So it may be a bit slow, but I don't know if it's really slow due to this compilation phase here. but still it's quite comfortable to work with this one. Good. Going next. So next is Markus Holzer, and right. Ooh. Yeah, I said ooh because I like the size of this program, but I cannot like catch it immediately how it works. So right, let's start with the last line where everything started. So it says, right, so okay, it says something that is returned by, wow, by the way, notice so that basically this C is the function defined here, and there are no parentheses here, but nevertheless these are the arguments that go to these parameters, right? But the thing is that you can, so see what you really have to look at is that this gather happens outside of the function. So it's not like this gather is inside the function, because take is inside the function, but gather is outside. So you see, so you call a function, you take something there, and around that function you can use this gather, obviously, right? After that you again make unique, but this time it's basically string concat. No, so it's not string concatenation, it's just smart match, right? So so I think this is even better than the previous two versions. So it just, I still don't like that you have to type so many characters, but that's actually the check that you have to do to make between two lists, right? So you have two lists of integers, and basically you use smart match to say if they are equal, right? In our understanding of this uniqueness, right? Okay, so the function itself, and you see, so it's called recursively. Actually, you see, so here originally we passed two values, the amount and the coin types, but here on the recursive call we add more things which will all land in basically this array that we still pass further for each of the items, and we take this sorted thing. So yeah, again, I'm afraid I cannot explain how this works, but if the sum is less or equal than the desired sum, then we take basically the current combination, if it's the size, if it gives the size, and after that, so after that we potentially can take, again, this take will be used inside this call, and it will be gathered to here, right? And after that we just say that. Okay, so let me run this function, this program, Raku, big Raku, Markus Holzer. What's wrong? It's wrong directory. Raku, Markus Holzer, Raku chair 1. Right, so here are the combinations. There are 6 of them, and they are kind of correct, right? I believe, right. Interesting. Okay, good. So Noud. Right. So here's the code. So again, we have this built-in input data and this coins sum function, which takes the coin types and the amount. If the amount is 0, we return an empty thing. Actually, yeah. So let's maybe look at this Raku. What's this? What? This is an array, and its first item is a list, right? So this is a list, this is an array, and if you will do it like this, it's still an array, but yeah. Okay, so that's the return result, I believe, right? We return this, and for all the coins, if this coin is less than sum, so we can use this coin, right? Then again, we recursively, basically it is similar to the previous solution. We recursively call the same thing, and we reduce the sum, the result amount, by the value of the current coin. And so these are really brain breaking algorithms, but nevertheless, from the Raku syntax perspective, I think everything is clear here, maybe except these. Probably parentheses are a bit redundant, but nevertheless, so we append an array, and this one, yeah, that's like everything here goes here. Right. Raku, Noud, Raku, Jeon. So here is exactly the same output as the previous, right? Well, except the parentheses around. Right. Good. Simon Proctor. Let's look at this solution. And right, so here's the solution, and the first thing to look at is this basically instruction. So there's this dynamic variable submain opts the hash, and we assign this key to this hash named anywhere. And actually, yeah, in one of the previous weeks I complained that you cannot put named parameters in the command line after the arguments, the positional arguments, but actually this one changes the situation. So you can assign this, and after that you can put named parameters after the others. Right, nevertheless, so there's main function, given the amount and list of valid coins, show all the combinations of change. Right, so there's the amount first, then the coins, which have to be integer, and at least one of them there should be. Right, so, and we are printing the array called change, which is built using this make change function, which accepts basically the same arguments, but there are two multi-versions of this function. The first one is when the amount is 0, basically you return an empty list. Yeah, there's nothing to return as change. But if it's non-zero amount, then yeah, so there's this hash somewhere. The key is the amount. So I believe we are going to call this function recursively, and indeed, so here it is. So we okay, so let's look at the amount. Where do we change this one? Amount, I don't see whether it's like cache amounts, yeah. Right, so yeah, so basically, yeah, we did not modify the variable itself, but we just call the function with different argument, and basically with the amount, which is less by the previous requested one by the size of the coin. Right, so with so you topicalize the predefined result, or pre-computed result, and you return it. What? You return from this block. Basically, what does this do? That's an interesting thing. So you I return it from a function at this position. Yeah, okay. So yeah, the thing I forgot, but basically with it's not only just topicalizes the thing, but it executes the rest only if this condition is defined, right? So if there is already the pre-computed value, then you can just return this, and you can flatten the result, right? So if you don't have the answer yet, so you have to build this, and you prepare the result, then you grab the coins. You only take the coins which are less than the amount. Well, in our default case, 6 is the amount, and the biggest coin is 4, so all the coins will participate here. So this is the current coin type, right? You create the list. You try to make the change without that coin, and the amount is also less by this coin size, right? You only take the basically, yeah, so it's kind of repeating things. I mean, this one, you only pass the coins which do not exceed the amount, but basically I think here you can already check this one, right? Because it will, if the coin passes this filter, it doesn't mean that it will pass the filter in the second call of the function, right? Right. Then, wow, that's an interesting thing. Maybe we have to write a program for that, so to see what's there inside. So for example, my list is 10, 20, 30, 40, and let's just say this change, or even dd this. So we see, so expect position bottle int. So I wonder how this works then. So for list to another list, right? So basically this is like this, I believe, right? Yes. So we see, so that's an interesting thing. So yeah, by looking at this, you cannot understand what's there behind this loop, but basically this list should already contain lists. So on each iteration you will get this array, but I believe there's not big deal. It's not big deal to just use the scalar there, right? Right. You can still access separate elements there. Interesting thing. So this one, yeah, so it's list of lists, if I'm correct, because this is the sublist which we just flatten, and together with the current coin we will push to the result, and in the end this result will be saved in the cache for the given amount. But before that, this result is converted somehow. So for each value from the result, we sort probably the items in each list of lists, right? Then we use this unique, we saw this already, and then we sort it by the increasing length, and after that you actually save it in the cache and return the result. Right, really interesting solution. I mean, it's so there are two things to look at. First, there's multifunction for the trivial case, and the second thing is there's just the recursive call, and actually the third thing is this pattern, which I believe I've never met this before in other solutions, right? And definitely I've never used it myself. I hope, maybe yes. Okay, so let's run this solution. So it's Simon Proctor, Raku, Simon Proctor. So what do we need? We need basically the amount and the coin, and you see, right, so the amount goes first. Raku chat 2, amount is 61224. So we go to the next solution by Athanasius. So here is the solution which starts as the main function. So we take the natural amount, then the coins, they are again all natural integers, unsigned, defined, bigger than 0, and then ensure that this is a set of by removing n duplicate coin values, also sort the values. So my nil, what does that mean? So basically it's a map where the values are nil and nothing else, right? Well, interesting. So basically it's a set. There's no need to use a map here, right? It's basically a set. Is a set by removing, but you can just directly convert it to a set, right? Okay, so then you take the keys, you sort them as integers, and you convert all of them to integers and to unsigned in integer, and this is basically your coins. Then for non-trivial case memoization, vastly decreases computation time, right? So it's a thing that I believe there should be a module somewhere, right? Use memoize. And yeah, basically it's kind of the let's modules. Raku memoize search, this one I believe, right? Yeah, so it's port of Perl's memoize 1.03. It's basically kind of the cache, right? There's the function, there are some options, and stashes the immutable write time and wait, blah, blah, blah. Good. So basically this function is the thing that basically does the thing. So how does it work? So we call this with the amount, and we pass the keys. They are already sorted, so basically the reverse gives you the biggest coin first. There are possible ways to make the sum from the coins, right? And yeah, this function is the most interesting thing here, probably. So it takes the target value, the target amount, and the coins, and returns the number of combinations, I believe, right? Because it's just count combinations. It will not give you the combinations themselves. So we take the coin, and if there are more coins still, there are more coins to process, as many coins as possible before you go out of the limit. So you set the new target by decreasing the original amount, and if we reach the 0, then good. If not, then we call this function recursively. Sum plus so the sum basically is the number of combinations which will be returned, and basically you increment the combination here if you reach. If not, you just call this function recursively and you add up the number of combinations returned by this function. But what this function can return basically, so this either it will be incremented a few times in these loops, right? Actually, in this loop, there's only one loop, or it will be 1 if you can just use this only this coin to basically, it's again the pattern in Raku, you can just use double % and remove this. So if you can use only a single type of coin, then this sum is 1 immediately. So there's 1 combination, right? So the answer is 1 in this case. Okay, so let's run this program at commas. I believe this is something for printing, right? Yeah, at commas, commatizing numbers. Wow, in Raku, really, there's the task to how to commatize numbers. Raku, wow. So there's this one. I see. So it prints, I believe, this, right? Good. Okay, so let's run the function, the program, but before that, let's see. So it needs -s, after that the coins. So Raku, Athanasius, Raku, ch1 -s, s is 6, and the coins 1, 2, and 4. Ooh, yeah. Zef install memo eyes. Okay, but before we can proceed, let's just move to the next solution. The next solution, where it is Colin Crain. Let's just look at this solution. Right, so here we are. So the default amount, there are no default keys in the header, but there are some additional things here. Basically, it's default keys if we didn't provide it in command line. Then we sort the key by so you call the method on the variable and you assign the result back to the same variable. So basically you just sort the variable in place. Get coin groups, and that's it, right? So after that you've got these solutions. Probably it's the global variable which is modified, right? So see, you push it, you modify it inside this get coin groups function. So that's the amount, that's the group, that's the bag which is coins originally, but probably, right, so you call it recursively and you pass the smaller coin bag, the thing that I called wallet in my case, in my program. And so that's basically the bag. You only take the coins which are which do not exceed the amount. That's that's an obvious thing to do. But then in each case, if basically there's nothing in the bag left, we return. But if there is something, we loop over that and we just grab everything which is less than the current coin, and again decrease the amount and call the function recursively. We saw this kind of pattern in the previous programs. Right, so let's run this. If we can run the previous solution, there are 6 possible ways to make the sum, right? Then we are calling this Colin Crain solution Raku ch1. What do we need? We need nothing, but there are 7 ways, but I want the same 6, 1, 2, and 4. These are the 6 different ways to make the sum of 6, right? And you see, so he's numbering this. I wonder how these letters appear there. Letter prefixes. Interesting. That's interesting thing. And actually, I really like this because there was one of the solutions in the earlier weeks of Perl Weekly Challenge, when it was called Perl Weekly Challenge, where you have to count Excel columns. Basically, this is how you can do that. That's smart. I like this. So if there are like more than 26 cases, you will get these Excel typed named. Good names. Right, nice thing. Okay, going next, Javier Luque, coin combinations that the main function in this main subroutine, and it takes the coins, the sum, and the bag, which is a copy. Parentheses probably not needed there, right? So you scan the coins, you take it to the bag. If the bag contains smaller amount than the amount we need, we call this function recursively and try to add more coins to this. If this bag is already correct, then you can just print this, right? And I wonder, where do we use this found? Unless found. So you print this. If it's not, okay. Right, so let's run this Raku, Javier Raku Chair 1. Output 6 solutions. Good. Laurent Raku number 1. So find sum, and basically, so that's the different pattern of getting the parameters from command line. Squish. Is it something like unique? And you direct. So interesting. So yeah. So there's this args global variable, well, the dynamic variable. So you remove the target from it, and everything which is left is basically the coin types, and you immediately sort this thing. So you can. So basically, this coins array is already sorted. Right, so find the sum. So it's that's the functional programming approach, I believe, right? So you start with this one, and definitely again, so you're calling this recursively. Actually not. That's actually yes. Why I didn't find this? Right, so yeah, you call this recursively. So the start, what is the start? The start is basically the amount, right? Allocated so far, and this is the coins in the combination, I believe, right? So if start is the sum, then we're done. But if not, you take the last thing from the allocated so far array. If defined, I think there should be better pattern for this, right? And then you take the coins which are bigger than the last coin and repeat the procedure for them. So basically this is similar to just the previous solution, but just it starts from the different end, different direction. Right, so let's run this Raku, Laurent Rosenfeld Raku Chip 1. So we need 6, 1, 2, 1, 2, 4. Yeah, 1, 2, 3, 4, 5, 6 solutions. Nice. Mohammad Raku 1. So there are some coins, but again Mohammad is using the string and passes it here. Sum, right, so coins sum. Here's the program. So yeah, basically this is all this is just to split this string into integers, and the number of the elements, return 0 if some conditions are trivial. Right, so then you create the matrix. The matrix, oh, wow. So for example, I have like some array, and I can like access the fifth element, right? But I also can do it like this. basically there's no difference. So I believe this one, I don't know why we need this, but yeah, nevertheless. So, but that's the matrix. Sum of 0 can be achieved in one possible way. So all this is, so I mean all this, my size is 10, say for this. You can do it, say, for size, right? That's the same thing. But then you scan again the same pattern as here, and you scan it. So yeah, basically you're trying to fill the matrix, the square matrix. If I'm well, not the square, right? It's include current, exclude current. If the current coin is so this is the index. This is the sum, right? So these are the coin indexes, and this is the sum. So you just fill this. So you just increment the required sum, and you try to do something with that. And if this coin is less than sum, then you include the current coin, right? And otherwise you exclude it. Okay, then you save in the current position the number of these, and then you return the matrices on the previous size, on basically the maximum size for the given amount. So see, so the first column is the length, right? And then it's the amount. I can't say that I understand the algorithm here. Raku Mohammad, Raku Jeon, Raku coins 1, 2, and 4, possible ways to achieve the target, right? But what I want to, why do we need this? I want to just look at the matrix, right? So where can I do this? Probably we call this once. Yeah, so we're not calling this recursively, so we can just print matrix before we return the result. Raku T, blah. Yeah, so this is the collection. So this is, I don't know why does this. I understand now. So you should remember there was a solution, something like that, where we'll just fill this with zeros, and then you scan this, and then the last thing is the result, right? Okay, going next. 2 solutions left, and we have 2 left in the beginning of the list. They are so big that I decided to skip them for now. So okay, so subset of coin where integers are bigger than 0, combination of coin sum. Where do we call this? So there it gets the sum and the amount. It's defined coin. So we see, so the new subset is called coin. Right, so, and what do we print there? And we print the combinations, right? The number of combinations, and yeah, basically we dump this thing, but this is coins, right? You see, so so this is instead of map, you can use this one. You basically call .int on age, and probably you can even do it a bit simpler. Probably maybe not, because you are saving the result in the same variable. Right. Okay, so the main function reset rest of coins, first coin, rest of coins. So you take the first coin, then the rest. Why you're taking the rest and the first? Right. So it's decreasingly, we sort by decreasing the value. Interesting pattern. So not just return empty parentheses, but empty parentheses dot return. Right, then max_nog. So this is basically the maximum number of coins that you NOC, number of coins that you can use of the this given first coin to represent the amount. But there may be something left, right? So then you maximum number of coins, that's the sequence decreasing to 0. the change, basically, this is what is left by this division. And I believe what happens if, like, immediately this gives you the sum. Then you take these coins of this amount, and and if change, so if change is bigger than 0, then these coins are never needed, right? So you probably can move it a bit back, a bit somewhere in a different place, but you still check it here. Okay, probably not. Right, so if there's something left, then you recursively call this function, and what do you pass there? So no, so wow, that's with where the function is called, and if it gives you some result, but wait, docs, but with, it's not just, so okay, so with, let's just look at this control for with. So it to defined, right? So this one should be defined, but I wonder if this one is returned. It's not defined, right? Okay. If elements, then you map. What do you map? You map the result of this as the. So so you call this function, and in the case it gives you some non-empty result or defined result, you topicalize this result, and then you call this dot elements and dot map on that result of that function, right? Right, then you map this for the rest coins, you append it to the result. What is the result? Result is only filled either here or here. So if there's something, you push this, or if there are some elements, then you push those coins still. Okay, let's maybe just run this, and Raku, not here, Raku, Jeon, Raku, 1. So we need the amount, 1, 2, 4, the coins. There are 6 possible ways. Good. And you see, so this is possible ways. Basically, you see, so this output is generated by this line. So you convert all the items in this array to an array and just print them. Okay, right, and the final solution here in this list, Roger Bell West. Right, so there's a coin sum with this example, and 4, you push the possibilities of, so what is M? Where is it used? It's used here. So you take this division, so basically that's the maximum number of the coin which can appear in the output, right? So okay, you fill this while off. Whoa. Yeah, I believe I cannot just immediately understand what's happening here, but the thing is that this function is not recursive, so it's okay, and you do this infinitely, and you break this loop when you basically exceed the maximum number of coins, right, that can fit the result. And what do you do with the sum? So if this is the sum, you take it to the result, and where, I wonder, where is this out here? There's no out here. Yeah, but you're taking this one, right? Yeah. So you take this one, and you increment the number of coins in the bag, right, in the wallet. And finally I is, so you increment this I. Okay, I think variables may be a bit short to understand what they mean without knowing the algorithm, but I believe this solution works, and I believe if you run it, Raku, Roger Bellast, Raku, chair 1, there's the test case, it should be okay. Okay, right, so there are two solutions left from the beginning of this list. Let's look at them, and this is Jan Krnavek and Luca Ferrari. Maybe go to Luca solution first. Right, so here it is. So the main function, it takes the amount in the coins. Solutions is find solutions. Right. Solution choice. Okay, and let's find these solutions. So the find solution, sum and coins, my solutions, and all the one coin solutions. Right, so yeah, this is what you can do with a single coin, but it's not always possible, right? Definitely. Right, now inspect all the other cases. And the last step, decompose every number in the solution into other numbers. Why? So, right, let's look at this. So you grab the coins, which you cannot use as a single coin solution, right? And you sort them by decrementing amount. This is the and you loop over those coins. So you skip the coins which are basically, you can add this solution here to this graph, right? Or add another graph here. So you skip the coins which are too big for the given sum, and you take this current coin, right? Then you take the coins which is not the current coin. That's an interesting thing. So what? So if it's an integer, why? It's a smart match. Probably like equals operator, or probably, or maybe not. I don't know. Again, you scan them in decreasing order. Then you take the sum. Try to add the same number over and over again while you are taking this sum, while current sum plus dollar underscore is right, is the topic of this for loop. And this is basically the coin, right? So you take this coin. If you found the solution, use a new array to clone it. So I can write. So you create a new array, push array new. Wow, interesting. So you see, so you can use this column twice. So like with parentheses, there are like parentheses around this, and then another set of parentheses around here. And but this one is already not the argument. It's just the what is the adverb, if I'm correct, to remove the thing from the array. Yes, delete. Yeah, it's adverb. Okay, next. Then, okay, so last step, decompose every number in the solution into other numbers. So there's the solution, and there's decomposed solution array. Again, again, this pattern with two adds, but this is list of lists. This is just list a single thing. For LM switching index, if current coin. Why is it like tilde? And here, so all the way, so and here is again, instead of comparison, we're using tilde. But yeah, I don't understand why. So Raku like 5 tilde 5, right? 5 tilde 10. It's false. Right. And the new solution again. So this is the copy of the array. That's an interesting pattern, by the way, right? Instead of just cloning, just create a new array with the with some initialization list. New solution switching index, so the flatten the repeating thing, so that you can use this current coin and fill. Okay, so probably you decompose, like if the coin is 2, you fill it with coins of 1, right? Raku, Luca Ferrari, Raku, chair 1, and I believe we need some input. Like 6, 1, 2, and 4. Yeah. I wonder this decomposed thing. How do they enter unique solutions? So now build something. Okay, so now we're using these solutions and unique and decomposed solutions, and they may contain something similar, so we create the unique solutions hash and just take the values of this hash as the result. And the only thing that it's you see, so it comes in different order every time you run it. Okay, right. And finally, the solution by Jan Krnavek. Right, it's here. It's also a big solution. Actually, it's not that big now. So there's multi-main function. Is it only one? Yeah, the main function is one, but there are more multi-functions like iterator and coins sum. So let's see. Ooh, wrap. Ooh. So that's yeah, kind of thing in Python. You can wrap the function, and actually in Raku you also can do that. Wrap and unwrap. Wrap handle. So creates and written by wrap. It is only used to unwrap. Either call unwrap or no. As okay, so yeah, documentation is a bit like short for this interesting case, but I understand that basically you wrap the like f function and right. So yeah, so that's the pattern of how you use it. So you print something before and after the function, and call same basically calls the wrapped function. After that you can restore this. Okay, but I believe we're not restoring. Why do we need it, right, in this program? Okay, so you wrap something around this, and oh, note is kind of say but prints to std area stream, right? When capture, what's the capture? Here's the capture, but why here? So if this one is a variable that contains a capture, then you do this. Ooh. So yeah, so probably we have to think of space after the comma, right? So it's different things. So we print the sum, the coins, the use from the capture, and kxxv. What's that? Really, I didn't know about that. So it's rollbaggy. Returns the sequence of the keys of the invoke count with each key multiplied by its weight. Note that kxxv only works for bagged types, which okay, so like output bbb back hash. So you take this spam eggs spam bacon and bacon eggs spam. So it's basically you convert like a list with non-unique elements to a bag, and then basically you can reproduce this thing again multiplied. So yeah, for string multiplication means repetition, right? If I understand this correctly. Right, call same. Yeah, so we know that we are calling this the function which was wrapped, basically this iterator, and this iter is a multifunction of 3 variants, which takes a caption with the first variant is the sum is 0, then another thing, and basically you just, oh my god. So that's another capture, right? We saw this thing somewhere earlier, and then finally probably the algorithm itself. So yeah, so this one is Unicode. That's good. Use back. So you so yeah, you call you decrease the sum by the first coin in the result in the coins, and you use this. So this is Unicode, this is not the Unicode, but basically, right, that's the set operation for the Unicode. There's a Unicode character for that. And the second thing, the second return value is another capture with coins. So yeah, so you pass captures there, and basically you see that's why you have this when capture. So when this is a capture, you expect that this capture contains these elements. So it's not a hash, it's a capture with the elements like sum, used and coins, right? Sum, used, and coins. Okay, so with this one, so if there's sequence, then you map that using the iterator, so it's recursively calls the function for each of the element in the sequence. Then you grab, so this is the Boolean check. You grab the things where there is these coins, right? Item, and then you grab only the things with a positive or zero with non-negative sum. Can the sum be negative? It's a bit weird. Okay, coin sum. Where do we have this function? A coin sum. You cannot find this. Right. Here it is. Is right. So we took this one. Actually, only if it's logging. So that's an interesting thing. So basically, if log, you wrap the function, but all the rest stays unchanged, right? So you can just execute the code, but this function will be wrapped. That's a good pattern, I believe, for debugging. You do not modify the main program, but you just wrap some functions before you run the program. Okay, then there are some tests. There should be some test module, I believe, somewhere here. And coins sum. So yeah, basically you call the coins sum function. Here it is. For the empty sum, you return the empty result. For non-empty, there's another version of this multi-function. And deep two sums are 0. Coins mean coins elements. So you take the minimum coin, you try to prepare the amount by the smallest coins, but then you append the number of. Then yeah, I don't want to understand this solution, I believe, but nevertheless. So let's look. So there's the sequence with this iterator thing. You call this iter. Yeah, so this, you call this, and this function gets this capture. Yeah, so I think I should stop here. I don't think it's a solution for this simple task. Okay, nevertheless, let's maybe run this. And so run Vambersh Raku 1. So what do we need? We need nothing. So right, I don't know where is. So this is the 6 sum. Right, this one, right? No. So there's so many tests output, but you cannot understand which one is which. So if coins, what are we calling this again? What's the point of calling this one? That's a log which again you cannot understand without. But okay, so from this solution, what I learned is that you can wrap the function for debugging. This is the thing that I want to explore further. Not now, but just in general. Probably that's an interesting thing. Okay, so that was the solutions of the first task of week number 75 of the weekly challenge. And the task was to find the coins for the given amount of change. So that's it for now. So hope to see you again in the second solution. I hope they will be a bit simpler solutions, but yeah, let's see. So yeah, stay tuned.